Good morning, everyone. Jim Chastain with EasyPower. This is our weekly installment of the refresher series for EasyPower tools. And today we're continuing the discussion on device coordination and in particular how to utilize the coordination features and tools when you're incorporating MCCs and panels in your OneLine. There are a large number of very sophisticated controls in the tools, and they can be invoked for standalone breakers and loads as well as MCCs and panels, and so that's where we'll be spending our time today. Good news is they're the same in any of these contexts, so you're going to be seeing a repetition of a same number of activities, if you will, so you should be able to hopefully get some good ideas on how to use the tools. All right, so we are doing these in bite-sized pieces as we go through each weekly session. We're specifically focusing on insight on how to use the tools and the capabilities on the tools, not specifically advice on systems engineering. Feel free to send questions via email or chat, and if possible we'll try to address them towards the end of the session. And by all means, if you can't, a quick note about how the audio sounds would be appreciated. So the focus for today is panels and MCCs and coordination and the options to coordinate with downstream loads. As a rule, arc flash incident energies are calculated to the top of the panels and to the main bus on the panels and the MCCs. So if you have any loads in either that you need to label, or you need to know what the incident energy is on that particular load, or you need to coordinate to it, then you need to outboard the, I shouldn't say that. It's just for calculating arc flash and incident energy, you need to outboard that particular load in the panel. And we're going to do that as we go through this discussion. Last week, I think the webinar ended abruptly, at least the part I was recording. So we're going to be repeating many of these specific techniques, and because they are used in each one of these steps that I'm going through. And we'll actually link the two webinars when we get them set up online on the website. So as we mentioned before, time is a key element in calculating arc flash incident energy. The advantage of Power Protector, which is the EasyPower coordination module, is it allows us to visually identify elements which affect time and how to coordinate those elements by doing adjustments to their performance and trip curves. It works with individual elements or a complex combination of elements, and again, it allows us to connect the performance of a protective device with the loads involved. A quick refresher on time current curves. This is a typical motor starting curve, the thin blue line, and it is controlled by all the elements that we use to set up in the motor parameters when we describe the motor in the OneLine diagram. And so this particular current level, the axis are current across the horizontal axis and time on the vertical axis in a log-log scale. This current level is set by the full load current. This short blue line is set by the thermal damage curve, which is plotted, enabled with this checkbox, and controlled with these two time settings. The acceleration time, it determines at which point the high starting current drops to a more normal run current. And then the high starting current is a factor of locked rotor times full load current. And then for an asymmetrical offset, as the motor receives full voltage, it's controlled by the offset times the inrush current. So those are the connection between what we set up in data and what the performance curve looks like for the motor. Likewise on breakers, this is the TC trip curve, where anything to the left, any current for this amount of time, so if let's say this is 1,000 amps for 0.1 seconds, if we saw that event, it would be to the left of the trip current for this breaker and consequently would not cause the breaker to trip. On the other hand, if we saw, I take that back, so this is 1,000 amps, 100 times 100 would be 10,000 amps. If we saw 10,000 amps for 1 second, it would definitely cause this breaker to trip. The shape of this curve and all the plot points are determined by specifically everything that's input on the phase trip tab of the data dialog box for the breaker. Once we've decided the manufacturer, the type of breaker, and the type of trip unit, the sensor and the plug, then all the rest of this graph is controlled by the long-term pickup, the long-term delay, the short-term pickup, the short-term delay, and the instantaneous pickup. And as I mentioned, the advantage of Power Protector, it allows us to overlay these curves and then compare what's required for the motor operation and what's required to protect the motor, and we make adjustments accordingly. Okay, so with that little bit of background, let's get into the discussion of the tools. Here we have a system of kind of a typical distribution system where we have upstream protective relays, transformers. Here we're coming from 13.8 down to 480 volts, and then a bunch of loads on a piece of switchgear. So where I want to start is right here, where we have a standalone breaker and a standalone load. And what I want to show is the arc fault current for that this breaker is going to see if we have a fault on this bus. First of all, we want to see what the current is when we fault the bus. So I'm going to go to short circuit. So I've changed the focus from database editor to short circuit. And once I'm there, I can fault, so that means I've started with a clean one-line diagram, and I can fault the buses. And as I do this, I reflect incident energy when I have the little lightning bolt, or I can show branch current if I select the half cycle. All right, so let's go ahead and look at incident energy and highlight this breaker and this load and this bus, and go to the coordination focus module. And by virtue of having these elements selected, we're going to plot the TCC curve, and now we come up with this particular display. A couple things to note: that this one-line diagram is a subset, obviously, of what's on the main one line, and as we make changes here, it doesn't affect the one line itself, but it does affect what's being displayed in the inset on the one-line diagram on the TC curve. We have the title block at the bottom, which can be customized to show labels, dates, text, logos, and it's displayed at least on the screen by checking this little box. If we uncheck it, we give ourselves a little bit more room to discuss. Here is our motor start curve. Here's our breaker curve. This other blue line here, now you may recognize this is the thermal damage curve with the circle and the blue line up and to the left. This is the damage curve for the cable, which is part of this installation, which I've highlighted. I'm going to select it and delete it from this particular display. Okay, what I really want to focus on is this tick mark and the settings on this particular breaker. As I double click on this tick mark, this is showing that this is an indication from BL3, and as I hover over it, I kind of go back to selecting this. As I hover over it, the information box tells me that this is the asymmetrical momentary current for BL3. So I double click the tick mark, which opens up the temporary dialog box for the breaker. I'm on the short circuit tab, and if I go down to the middle section, I see that we have selected a tick mark for momentary current. I'm showing 8,800/968, which is essentially what this number is. I can also display interrupting current and 30 cycle current, and if I apply these tick marks, I see now I have three different locations, this being for the half cycle, the half cycle current, this being for the 5-cycle current, and this being the 30-cycle current. Let's kind of go back to the OneLine diagram, fault this bus, and I noticed that I have, let's kind of spread this out, I'm showing 6,501 amps, which doesn't match any of these numbers. What we're looking at here is half cycle current, and if I look at the TC options and the units are involved, I'm displaying the symmetrical current. So we have the ability to display symmetrical, asymmetrical, and both of them together. And so now as I display both on the OneLine, I see now that I have 6,500 as symmetrical, 6,704, which is what we have for asymmetrical during the half cycle. Okay, so now we're connecting the tick marks here and what we're showing on the OneLine diagram and the units involved. Okay, all that's nice as well and good, and that's important as we're looking at different elements of the system. I also want to show the current, the fault current that's displayed or utilized for arc flash incident energy. Okay, let me take a step back. I'm going to close this. Not going to save it. We're going to calculate incident energy from the OneLine diagram. I'm going to fault the bus. I'm in short circuit focus, fault the bus. I get incident energy. I'm going to arrange for arc flash, which shows me the arc flash hazard report. These are all the elements that are used for arc flash calculations. We're showing a bus fault current and an arc fault current. And so for posterity or for reference later, I want to export this to Excel and just stash it over here on the side, and we'll come back to it. One more thing while I'm here, I want to also look at the short circuit options and understand how arc flash is being calculated. For starters, we're showing that it's excluding main and we're using momentary current. So we'll come back to this in a second. Now I want to go back to where I was before I came back to check on arc current. Coordination module, plot the TCC curve. Let's go in and look at what we're plotting, and let's go ahead and take the tick mark off. Now the other thing that we see on this set point is that we have TCC clipping using momentary current. Let's select none and apply this. We expect to see the tick mark go away, and now we see additional display of this performance of the breaker. We're going to fault the bus, which is again downstream of the breaker. We see that we have a symmetrical fault current of 6,501 amps. Come over to the curve, right click, insert arcing tick mark. And what this gives me is 100% arcing current for that's going to be going through BL3. And now if I go back and look at what was utilized during arc flash calculations, I'm seeing bus 5 would be having a max arc current of 5,185 amps, and consequently, and so this is a little bit less, so I need to figure out where that's coming from. At this point, my chore is to make adjustments to this breaker to stay to the left of the thermal damage curve and to the right of the motor starting curve. And at this point, we can see that this will be the incident energy. If I look at you guys may not be able to see my label down here at the bottom. So the cursor coordinates is going to show up on this bottom bar. And so the breaker will start to engage at this point, which is about 0.1 seconds or 100 milliseconds, and it will clear at just about 200 milliseconds. So that's what's utilized in arc flash calculations. All right, if I want to save this, if I want to print this in a report, it's all built into the tools. So essentially we've shown the arc fault current on BL3 on the TCC curve. Let's close this and let's go to the next one. All right, so we've done this part. Which breaker controls incident energy at MCC1, BL4A, or the main in MCC1? So again, we're going to fault this bus. Let's go to short circuit again. Fault this bus. We see we have an incident energy of 8.4 calories with an arc flash boundary of 58 inches. If we look at the arc flash hazard report, we see that the upstream trip device is BL4. So why isn't the main breaker on MCC1A being effective? For this, we go back to the options that we looked at earlier, and the arc flash hazard tab, we see that we're using IEEE 1584 as the model, but we're excluding the main. If we know in fact that the main in this panel is isolated from the secondary bus, such that the upstream voltage isn't exposed to a worker on a hot bus, then we can include the effectiveness of the main breaker, and as we change the setting and apply, you'll see that the incident energies come down to a more reasonable level. So the reason to exclude the main has nothing to do with worrying that this breaker won't be effective. It has everything to do with the physical isolation between this breaker and the rest of the system. Okay, finally, so now I want to use, to see the difference between what these two breakers are set at. So let's go highlight the MCC and the breaker, go to the coordination focus, plot the TCC, and so what we see here is, here's the curve for BL4, the curve for MCC1. Let's go ahead and take off the title block and blow it up a little bit. All right, the same kind of thing here. We've got two tick marks, one for the main, one for BL4. And what I'd like to do is fault this bus and see where my incident energy is, where my arc current is. And we see that right here is where the arc 100% arcing current on that bus would be exposed to the breakers upstream. So what I want to do is say, okay, what if I select this curve, hold down shift and select that curve, I can create a difference calculator, and now it shows me at that current I have a separation of these two breakers of 155 milliseconds. Now that may be something we want to adjust or not, and as we do it we can see what the change is on the difference calculator. Okay. Any questions about that? All right, pretty straightforward. Now let's go to the MCC panel and panels and see how this kind of fits together. Now what we just saw on this one was calculating incident energy at the panel main bus. What we want to do is calculate incident energy and coordinate against a motor that's outboarded, which we've done here, and we've set this up as a sub-panel when we labeled this inside the MCC controls. So what we want to do is coordinate all the breakers and the largest motors for the MCC and this outboard load, outboard large motor. So we're in coordination focus. I highlight the motors, the panel, and the upstream breaker, and I'm going to plot the TCC. Okay, it's a little busy, but if we start looking at what's going on, we see that we have, here's MCC1 row 2, which is the breaker that we've outboarded this motor to. We see MCC1, which is a breaker for an internally described motor. Let me back up one. Bear with me here briefly. If I go and see how we set up MCC1, We have an incoming breaker that's been characterized. We have one motor set up with a TCC, and its protective device has been characterized and set up. And then we have a second motor, which we set up as a sub-panel and outboarded it. And although we do have the protective device set up, it does not have a TCC curve because the motor is outboarded. So this motor actually has a TC curve with it. So that's why we have two different settings. So we have row 1 is going to the internal motor, row 2 is going to the outboard motor. That's not confusing enough for everybody. All right, again, select everything, go to coordination, plot the curves. Okay, just to eliminate a little bit of the confusion, what I want to do is coordinate for this outboard motor first, which is row 2. So I'm going to take off the row 1 breaker. Now this is the starting motor for row 1, so let's take it off. So I'm just going to highlight and delete. And row 1 breaker I want to take off. Highlight and delete. So what I'm looking at now is MCC1 row 2, and we can ignore this guy, and my main breaker, and then the upstream BL2. So these three breakers are the ones that have to be coordinated for this particular load. If I highlight this bus and fault it, right, it brings back my breaker that I'm trying to ignore, so I'm going to get rid of him. And what I want to do first is, so this is the motor that we're coordinating against. Here's my row 2, which is my first breaker downstream. Here is the upstream breaker, so I want this to trip first. And I want to show arcing current for this particular motor. So let's kind of come back and get rid of some of these tick marks and this extended curve, starting here. Okay, again, this is row 2, so this is the first breaker upstream from the load. Let's take off the tick mark. Let's don't clip the curves. Let's apply that. And now I'm going to right-click on the curve and insert an arcing tick mark. And it says it can't do it, so let's go help it out. Oh, I'm looking at the wrong one. This is MCC1 row 1 again. Okay, row 2. All right, and so that's why you got to be a little bit careful with this. What you see here is this triangle is the 100% arcing current for row 2, and because I want it to be the first one to trip, I'll bring down its trip characteristics or its set point. So now I have separation between row 2, the main breaker, and if I look at this, I also want it to move this set point a little bit to the right of this curve, and it keeps recalculating my arc current. Once all this is said and done, I want a difference between these two curves and calculate that difference. And then my third curve, which will be so we'll set this up over the voltage fault current, the arc current. Okay, and so when all is said and done, I'm going to save this curve because it takes a little time to kind of get there. And here's what it looks like after I get a little bit more, spend a little bit more time with it. So I can see I have coordination now between the two curves and the motor that's downstream. Okay, one other point. So I'm going to close this TC curve. I'm going to close this TC curve. One other point that I wanted to make, and it really goes to this, the 85% setting on the breakers. And this, I think, is pretty fascinating. Well, it's important to understand. Again, we're showing the BL3, which is the breaker upstream, and I'm going to plot none of the tick points and have no clipping. I'm going to make this a little larger, and I want to display the, okay, now I like it when I make mistakes, all right? I'm saying I want you to insert the arcing tick mark. It says, okay, you need to just fault a single bus. All right, you're right. Let's go back and fault the bus, and now it shows my arcing tick mark. Again, it needs to know what the bolted fault it is that it's trying to protect. All right, what we see here is 100% arcing current, and if I calculate the incident energy over here, it's 4 calories. By adjusting this slightly higher, you can see the tick mark changes between 100% and 85%. And as I do that, the incident energy is automatically updated in the OneLine diagram. Difference being, and this is the reason why the IEEE recommends checking both the 85% and 100% of the arcing current based upon the settings that we have in the protective devices. In particular, MCC breakers have a very steep drop and inflection, whereas if we have a current set at this point, or at least the arc occurs at this particular current, the breaker may engage at this time, which is somewhere over 1.1, 1.3 milliseconds, 130 milliseconds, but it's not guaranteed to clear until somewhere up here, which is up near a half a second. So this is much more unpredictable and consequently a much worse setting point than if we just set it a little bit lower and make sure that the 85% is set, of the arc current is clear of this particular knee in the curve. So here now, as far as worst case calculations with this particular setting, the breaker has a potential for still engaging at the same point, 130 milliseconds, but it looks like it's guaranteed to clear well before the 200 millisecond point. Okay, all that can be derived and displayed visually and is important for anyone trying to do mitigation and coordination for any downstream load. So obviously once we've got this particular breaker set, then the next step in the procedure would be to then to coordinate the upstream breakers and protective devices against it, knowing that we don't change the BL3 set point because it's been set up for the load. And then if we reference everything from BL3, we can see that we have the potential for doing, again, fault the downstream bus. Insert the tick mark, and I'll fault it again, and then go through the whole procedure with the upstream breakers. So we don't want to do clipping, and we want to see where things are going to intersect. Same old, same old. Fault the bus. Here's my trick clipping, and I want to highlight this curve and this curve, show my difference calculator, and the difference at that current now will give me almost 2 seconds. So I have plenty of room now to make an adjustment to this particular curve. Now, curve adjustments can be made by clicking and dragging, or as we've discussed before, I can change the shape and settings on this curve by making adjustments to the control dial settings on the motor itself, on the breaker dialog box itself. And so as we make adjustments, we can see the shape of the curve and thereby influence what the difference is between the isolation and know that we have coordination for everything downstream as long as we don't change this particular breaker. Okay, any questions? We've kind of gone through, so the main point has been how to display the arcing tick mark, how to display the symmetrical and asymmetrical current. Again, when we're talking about a relay, and so this particular tick current is for relay 2-1, and we'll cover this more in next week's session. To be able to make adjustments here, we can drag and move the curve on the TC curve, in which case we'd be moving, I guess I got to find it first. Yep. And I need to work my way up. It's actually kind of silly to jump all the way up to the relay when I haven't covered the breakers downstream. Okay, so next week we'll get into relays and coordination there, including ground current settings, and I think that kind of covers the material we were shooting for today. Any questions? Appreciate everyone attending.